we're going to maximize the range of a projectile. So what that means is we're going to launch a projectile and we want to get the greatest distance that it actually goes. Well, first let's find what equation is useful for the range of a projectile. Well, we'll start with the Fab 5. V final equals V initial plus AT. If it's launched from the ground, it'll go up a time t and then come back down another time t. So we know that the total range is actually going to be proportional to 2 times t. Okay, so t with the time it takes to get to the max height. So remember that our beginning velocity in the y direction is going to be Vy naught. That'll be based on V naught times sine theta. And of course, Vx is constant in the x direction. So again, Vy is going to be our beginning velocity vector multiplied by the sine of the angle. So we know at max height, the velocity in the y direction will be 0. So we'll start that off with Vy. Well, actually, let's go ahead and use the sign right away so we don't have to rewrite this again. So we're just going to say V naught sine of theta. Okay, and that's going to be minus the value of g times t. Again, t is going to be the time it takes for this projectile to reach the max height. Okay, then solving for t, we have V naught sine theta divided by g. All right, now let's plug that time in for our x displacement equation. So x is equal to Vx times t. And what would that look like? Well, x is going to be V naught cosine theta multiplied by V naught sine theta divided by t. Well, remember, the range is actually twice the time. So then we've got to multiply this by 2 on top. Okay, and well, let's see what we got here. This should be a g on the bottom and not a t. Well, I recognize 2 times sine theta cosine theta as being a trig identity. Okay, and it goes like this. 2 sine theta cosine theta is equal to sine of 2 theta. So let's go ahead and simplify this then. X is going to equal V naught squared sine of 2 theta divided by g. Now what's our x? X in this case is going to be the range. So that's the horizontal range. So in other words, if I start here at my origin, whatever x displacement we go through when we finally hit back to the ground, that's going to be known as our range. Now we've not maximized that yet. We've just found the equation to find the range. Now in calculus, to maximize, you take the first derivative, okay, and set that equal to 0. So let's go ahead and maximize our range. So let's rewrite our equation now. I'll say it as range x is equal to V naught squared sine of 2 theta divided by g. Now what we want is the dx d theta for this graph, or for the projectile. So dx with respect to d theta. Well, v squared over g is just a constant, so we can put that there. Now we need to take the derivative of sine, and that of course is cosine of 2 theta. And now we must take the derivative of 2 theta, and that just equals 2. So I'm going to say times 2. I'll put that in parentheses. So dx d theta has to equal 0 in order for us to be at a maximum or a minimum. Okay, so that's going to equal 2v squared, v naught squared divided by g times the cosine of 2 theta. Okay, now we got to think, where is the cosine function equal to 0? Well, that's equal to pi over 2, right? But we're twice the angle here. So if I multiply that by 2 again on the bottom, that's at pi over 4. Okay, or that's at 45 degrees, which is what pi over 4 is. So we will maximize our projectile when we are at pi over 4. Well, let's go back, okay, to this equation here and plug pi over 4 in our equation here. So we're going to call this x max, or the maximum range. That's when we put pi over 4 into this equation. Well, putting pi over 4 in this equation actually makes this pi over 2. Well, what's the sign of pi over 2? Well, that equals 1. So we can maximize the range by doing this equation, v naught squared, okay, divided by g. So as long as we know the beginning velocity, and that's the vector, and we divide that by g, we would see that this value here can give us our range pretty easily. Of course, you should do a second derivative test of this equation to prove that you have a negative, and a negative for the second derivative test indicates that there would be a maximum. Well, just looking at this equation here, if I take the second derivative of this, the derivative of cosine is negative sine, and indeed we see that this second derivative test does give us a positive result. And positive meaning it proves that this is a maximum. So I need to be careful because this value is actually going to be a negative. Okay, the negative of the second derivative tells us that this is actually a maximum, not a minimum. If you don't remember that, look back to your calculus under your maximums and mins and how that's done. Okay, so that's how we maximize the range.